let's put L'Hopital's rule in action on some actual limits, specifically ones that we were able to do with old techniques. So for this type of problem, the limit as x approaches 7, the way we would have done this earlier is we would have said, that's the limit as x approaches 7 of x minus 7 over x plus 7, x minus 7. So then those would have canceled, and then when we plug it in, we get 3 over 14, which is fine. That's a perfectly fine way to do that. But let's try to do it with L'Hopital's rule. If we plug in 7 here, we get 0 over, so 3 times 0 over 49 times 49. So we have a 0 over 0 indeterminate form. So as a result, what we want to do is we want to say, all right, that's the limit as x approaches 7 of the derivative of the top, derivative of the bottom. So that's 3 times the derivative of x minus 7, which is just 1. The derivative of this is 2x. So then we try to plug in 7. 3 over 2 times 7, 3/14. Way easier, right? At least I think so. The second one's even more true. If we had this problem, the square root of 16 minus x squared minus 4 over x, and it's the limit as x goes to 0. What we would have had to do before is multiply by that conjugate. We would have had to say 16 minus x squared plus 4, 16 minus x squared plus 4. And by doing that, what we would have done is gotten the limit as x approaches 0 of 16 minus x squared minus 16 over x square root of 16 minus x squared plus 4. At which point we would have gotten, this would have all canceled, the 16s would have canceled, so we would have had negative x squared on the top, which then would have canceled with an x on the bottom, so you would have had x goes to 0 of negative x square root of 16 minus x squared plus 4. When you plug in 0, you get 0 on top, you get 4 plus 4 on bottom, so it's 0 over 8, so it's 0. Okay, great. But let's not do that. Let's do that with L'Hopital's rule. So let's start here. We want to say that's the limit as x goes to 0 of 16 minus x squared to the 1/2 power over x. Again, if we plug in 0, we get, originally here, you get 16, square root of 16, so that's 4 minus 4, which is 0 on top, 0 on bottom. So if we have it this way, then taking the derivative is a little more straightforward. That's the limit as x goes to 0 of 1/2 16 minus x squared to the negative 1/2 times negative 2x. That's all that chain rule, right? We bring down the power, subtract 1 from the power, multiply by the derivative here. The derivative of negative 4 is 0. And then on bottom, we just have a 1. So that really just kind of goes away. So as a result, if I just plug in 0 here, I get the limit as x goes to 0 of 1/2 16 minus 0 times 0 over 1. So that's just some number, that's just some number, times 0 over 1. So it's just 0. Right? Because it's 0 times a bunch of numbers. So 0. So look, to me this is way simpler than having to remember to do all the conjugate stuff. It kind of takes a lot of your tricks in your toolkit and reduces them down to a very small set, which by the way makes it kind of harder to teach this stuff later because you're so used to doing it this way. Anyway, let's take a look at this final one. So we have sine of 5x over sine of 2x. And the way we would have had to do this before is you'd have to be a little bit clever. You'd have to say, okay, well, that's I'm gonna say that's like x over x sine of 5x sine of 2x. Then what I'm going to say is that's the limit as x goes to 0 of sine of 5x over x sine of 2x. Okay, hopefully you're tracking with me here. And then what I'm trying to do is I really want this to be a 5x. So if I need a 5 on bottom, I need a 5 out front. And I really want that to be a 2x. So to have a 2x on top, I need a 2 on bottom. The reason I want to do this is that by the squeeze theorem, both of those are 1. Remember the squeeze theorem tells us that the limit as x goes to 0 of sine of kx over kx is equal to 1. That's sort of our sine x over x for arbitrary, not just sine x over x, it's sine of kx over kx. So to do that, we have to rewrite it in a kind of a clever way. So that makes this one 1, and that's just the reciprocal of that, so it's also 1. So that gives us 5/2. Okay, so that's a lot of work, right? Ugh. So let's try to do this with L'Hopital's rule. If I plug in 0 directly, I get 0 on top, 0 on bottom. I get 0 over 0 case. So what I can do then is I can take the derivative. I can say, all right, that's the limit as x goes to 0 of cosine of 5x times the derivative of 5x over the cosine of 2x times the derivative of 2x. But cosine of 0 is 1. Cosine of 0 is 1. So I get 5/2. Way easier.